Hello everybody, this is chapter 6.1, the Boltzmann factor. Um, so in this chapter we're talking about probability of a system. So when we have a system and our book represents like this, with a big box connected to a smaller box, where the system is our smaller box and our reservoir is a bigger box. Oops. Okay. Then we have exchange of, well, we'll just say stuff. It can be energy in our case. And of course, we're gonna say that our energy in a reservoir is equals to U sub R, and our temperature is equals to T. Instead, in the system, the energy is just equals to E. Now, just the way they call it, it doesn't really matter what happens. Anyway, the idea is if you have an atom, so here we have a nucleus with the electrons on the outside that go around. Of course, this is not the exact model, as you know. It's just a bar model. There's no probability. So the idea is that, for example, this electron right here will lose the energy and send it somewhere else when it can, when there's something else to receive the energy. Instead, this other electron will try to gain the energy and jump to the upper level. However, if there is no exchange, then the two electrons will be in um, these two states. But again, we have exchange of energy, therefore we have a jump of, of the electrons between the different energy levels. And as you know, the lower energy level, I'm going to call E1, is equals to negative 13.6 electron volts. The energy 2 instead is equals to negative 3.4 electron volt. The energy 3 is equals to negative 1.5 electron volts. Okay, and as I said, we are talking about finding probabilities. Therefore, we're trying to find the probability that an electron is in state 1 or 2. Well, when we talked about probability so far, we always used the um, the macrostates. So we always found the many macrostates there are in total, and then we divided our macrostates for one energy by the total macrostates. We multiply by 100 because we wanted the percentage. But that's what we did so far. However, now we don't really have a number of microstates in our case, but we do instead have still two energy levels in our case, for example, and we want to find the probability that the electrons are in one microstate instead of the other. Well, so the probability of the the probability of one state instead of another state will then be simply the division between probability of being in that state divided by probability of being in the other state. This state I'm going to call S1 and S2. So S1 will be the lowest, or S1. Okay, sorry, S2 and S1. I would like to put those. So these two are the uh, probability, and then we can just write the macrostate for S2 divided by the macrostate of S1, and we can use our entropy, knowing that entropy is equals to KLN over macrostates. We can rewrite this and say that our entropy is equals to E at the power of S, divided by K. So what am we substituting in there? Well, then now we can say that at the top we're going to have E at the power of S. We're here talking about the reservoir, so SR of S2 divided by the energy of, the E at the power of SR of S1. So what's the probability that an electron is on the second state compared to the first state? okay? Divided by k, divided by k. Now, as you can see, this is simply a division between two powers with the same base. So we can just say e to the power of s r of s2 minus s r of s1 all divided by k. And we can remember also by using the thermodynamic identity that ds, which is our change in entropy, which is actually exactly what we have right here. So we would have e to the power of change in entropy in the reservoir divided by k. You're just going to call ds is equals to, of course, r 1 over t times du of the reservoir plus p dv of the reservoir minus chemical potential mu dn of the reservoir. Well, we can cancel out in two terms. NR, DNR, which is 0. This one instead is not equals to 0, but compared to DUR, so DVR, divided by DUR will be equals to 0. So it's so little that it doesn't really affect us. So we can just say that DSR is equals to 1 over T times DUR. And again, here we're talking about the reservoir, but we can talk about our system as the opposite. Remember, if we lose energy in our system, we're getting it in our reservoir. If we lose in our reservoir, we're getting in our system. Therefore, ds, or system, is equals to negative 1 over t du of the system. Okay? Therefore, now we can rewrite this. Oh, actually, sorry. Here, we called u of the system as E, like I mentioned at the beginning. Energy, we just call it E. Just you'll see in the end, it just makes it just nicer to look at. So ds, or change in entropy, we're not even gonna put the underscore, will be equals to negative 1 over T times energy. Of course, we're talking about it as actually I'm gonna leave as this for now. Okay. So now we can substitute it in, and in our equation that we had right here. So instead of delta SR or DSR, we're just going to use negative 1T over E. So we have that our ratio between the two probabilities, or the probability of one state over the other, is then equals to just E at the power of negative E. In this case, we're talking about an S value. We'll see why. Divided by KT now. This is what's called Boltzmann. Let me show you. Okay, Boltzmann factor. However, we could, while it would be nice to just say this is not entirely correct. We have to manipulate this function and say that actually the probability, so this one is not entirely correct, the probability of S2 divided by probability of S1 is equals to 1 over Z times E to the power of negative E S divided by K T. This is the actual probability of finding an electron at an energy level instead of at another energy level. Again, it's not a very complicated value, but this 1 over Z is what's called a partition function that we will see next. And instead, the right side is what we just said, is the Boltzmann factor. So this is all you need to remember from this part. And then we're going to analyze the partition function in the next video.